And the second speaker is Professor Raimo Kantola from Aalto University. He's a professor at networking technology. During his career path, he also served at Nokia for impressive 15 years. He has held many honorable positions at the university. He is a pioneer of international education. His recent research interests cover cooperative security, trust, privacy, and software-defined networking. His talk today is about embedding trust and security into networks.
So I'll take a wider view on issues of trust, and what I'm trying to tell is that instead of pursuing the end-to-end principle that is at the heart of the internet design, we should start putting trust functions into the network itself and make the network communications trustworthy. All right. Let me see, how does this, if I do it this way. So basically the paradigm of the internet has been that anything that is not just an IP packet, it should be a function of the end system, and this is called the end-to-end principle. For example, security and trust issues, they should be sort of implemented in the end systems. But if you look at this more carefully based on generic cooperation theory, my conclusion at least is that implementing trust without support from the network is not feasible, it's not doable. Right. So this is a motivation, but I won't go into that theory in this presentation. So I'll talk a little bit about the cybersecurity threats that are current and relate to 5G and also some other systems. And then about cloud computing, because it's the change in IT is towards moving more systems into the cloud, and it's a powerful technology. It supports professional management of software and high productivity of the experts and so on. So question is whether we could use that power in order to improve security. Two views on embedding trust into the network. One is device-centric. So we have been developing this cooperative security concept that I just mentioned very briefly here. We call it customer switching, and then there's a sort of the wide area view of embedding trust into the network. Okay, and finally I'll summarize. So the new battleground in cybersecurity is the boundary between the digital and the physical world. Like these medical examples, they are on this boundary of the physical world and the digital world. But this boundary is of course much wider, and due to 5G, this will become ever wider because with the 5G technology, we can reach more and more devices, and we can put communications over 5G into control loops and what have you. Then what is happening is that consumers buy new gadgets to their homes, and manufacturers of the gadgets and say refrigerators or whatever, TV sets, they want to collect from the devices. So they say that, you know, let's connect them to the internet and they will have access to that data. So who owns the data and who can access that data is a big question. And when we have this data and we have this boundary, the question is who can hack this boundary? If the boundary is directly visible on the internet, then it means that anybody having an internet connected device can try to hack it. If hacking is possible on this boundary, then self-driving cars will collide, containers, you know, physical containers used for transporting goods on ships and trucks. They can drop to ground in harbors. Turbines in electricity grid can break down because of too fast rotation. Electricity grid can be messed up, and then the electricity distribution can be disrupted. In electricity, we are moving from stable, predictable, static loads to more and more flexible loads, and it's only a matter of time when we have as many as you can imagine flexible loads, and they need to be controlled nationwide. And of course, this is a huge attack surface and a huge number of attack vectors that open as a result if we build this sort of thing. But we are forced to do so because of the wind power. So basically my advice for medical sector and for banking, for this kind of industrial application is not to connect the stuff to the internet at all. Instead, we need to build specialized networks. We need layers of fencing for security in different places. Of course, we will have always some amount of security-related functions on the devices, like for example, this attestation. But at the same time, it's possible to sell to the end consumers, end users, devices that have no security whatsoever. So we need some ways of even securing such devices. And on this boundary, safety and security are very closely married and intertwined together. So if something is unsecure, then it's also unsafe. Right. In 5G, it's a new technology that is coming online from networks. Hundreds of thousands of base stations are already up and running in the world, maybe close to 1 million by the end of the year, maybe a little bit less, 500,000 at least. 400,000 in China alone, 5G base stations, a few thousand in Finland also. So this is the new technology, and over the next few years, we'll have more of this. So 5G is different from previous ones in several different ways. One is that bit rates that you can get out of 5G devices are much higher than we had before. Gigabit downlink, 100 megabit uplink. So they are very powerful also for attacking other people's computers. Another factor that is different in 5G compared to previous generations of mobile technology, it's addressing the vertical markets, corporate markets, industry, and all kinds of uses of 5G technology in the economy. So it's a surface where it touches the society is much wider than the previous generations. So health, traffic, industry, medical use cases, lots of them, and physical world hacking or physical world crime can be supported by hacking in the digital world, you know, because of these use cases, not because of the nature of the 5G technology per se, but because of the use cases. And then the question is, well, when do we see first people killed by accidents that were caused by digital means? Okay. And in addition to these, we of course have the classical internet security threats, the distributed denial of service, ransomware, espionage, and so on. Right. Cloud computing. Why is this important? It's because more and more of the IT applications that we use, they are being moved to the cloud. And why is this? The reason is cost saving in operational cost, and also having professionals manage the software further, rather than if you happen to be a small company or a medium-sized company, then you cannot afford to hire real security experts. For example, even a software expert, it might be sort of like a side job for somebody whose expertise is elsewhere. So if you then order services from the cloud, you get personally managed services rather than cooked up yourself. Okay, so highly qualified specialists can be then used to manage the software, and so the quality improves, and also the productivity of the personnel improves, and specialization between people increases, and that's why cloud is so important in IT. Now, because the compute element is or compute elements are integrated into the network itself, you could have a compute element on a base station, for example. So what we can then do is we can have a server close to the devices and close in terms of delay, round-trip delay between the device and the server. And as a result, then we can do things that were not possible earlier. We can do lots of stuff on the commercial side, but in industrial case, sensing and controlling the world could happen at the edge of the network. So you have an industrial side, maybe private 5G network there, and it has an edge cloud, and all the controlling functions would run on that edge cloud. We have a low delay between client and mobile, and everything works much better than running it somewhere remote. At the same time, maintaining this kind of arrangement is very economic. We can keep the devices simple, and as a result, if we need to duplicate some device, say in a smart grid, no problem. It's not an expensive device because we make it simple and control that from the edge cloud. So there are these war stories about shortage of cybersecurity skills. Like Ian mentioned, these people are extremely busy. I heard a presentation by a guy in the UK recently who said that there are 3 million missing cybersecurity experts in Europe alone, right? Think about this, 3 million. Question is, could we possibly educate these people so that we would have enough? And the answer is clearly that no, there are not enough engineering students that we could educate in order to fill this gap. Another data says that 350,000 experts are needed in the European Union. Even that number is too big for us to educate them. There are not enough universities and not enough talented students to educate to become security experts. The Finnish Information Security Cluster, it's an association of companies in the security area, says that 20,000 experts are needed in Finland. Also, this number is so big that it's clearly infeasible to educate this many people. So the solution, obvious solution to this dilemma is automation. And automation is possible if we use the cloud technology. Similar that it's happening in all kinds of office applications. So we would then need to move lots of the security functions to the edge cloud or to some level of cloud. So far, this has really not been taking place in security. One reason why this is so is that in Europe, we had this net neutrality regulation until last June that forbids the ISPs and the mobile network operators to do anything, any kind of real business with security services. filtering is not allowed. Every packet should be treated the same. That was the ruling. Now there's a new ruling that changes this, and it opens the door to new products. This is so that security in a wide scale could be sort of by cloud software, edge cloud or any kind of cloud software. For integrations, net neutrality was never an issue because this is not internet access service. This is something different. But still, sort of, if we run this industrial data over the internet, I think it is a bad idea, because then the data that might be quite sensitive, very valuable, is particular internet data, and the access point to the internet becomes target for attacks from the weak devices taken over by hackers on the internet. So it's always better to run it that data in VPNs. Unfortunately, several of the VPNs are also targets for attacks, and if you run it over the internet, and you have a subscription in the internet, and even if you run it then within a tunnel that is created by the virtual private network provided by the network operator, you are sort of vulnerable still. So in cellular networks, the issue of trust and security has been so far such that, or the approach has been such that it's all about the mobile network operator and subscriber relation, so that we have paying customers being served. And in 5G also that the end device is able to make sure that the base station is not fake, and the traffic is not captured by some malicious party. Alternative that we are working on is this cooperative security, where it's like the Musketeer principle that we try to implement, where sort of everybody for one and one for everybody kind of principle is followed. So all good devices, all benevolent devices share evidence and trust information, and then use it to block all the resources that are used by the hackers. So that's the idea. So this is a sort of an overall end-to-end architecture where we destination network. This could be a factory network, for example, and the destination network could be in the cloud, or it could be something else, maybe some control center network elsewhere. And then we have the public services, federated public services domain in between, and these end networks or customer networks, originator and destination networks, are isolated from the public services domain by trust boundaries that are actually cooperative firewalls. Cooperative firewall is one that can ask questions, make requests to other parties before it makes a decision whether to admit a flow or not. Okay. So if this cooperative firewall resides in the telco cloud, then it doesn't really add delay, or if it resides in the edge cloud, even more so, it doesn't add a delay to the path of the packet. If it is somewhere in Azure cloud, then it might add significant delay, and the system wouldn't work that nicely. This firewall will execute policies. All flows are admitted by policy. And basically, if there's a socket, then there's a policy related to that socket in the TCP IP world. Device level policies would be governed by the users, and then the admin of the device, of course, will have its own policies, and they can be separately managed. So this is our implementation in GitHub. On the left-hand side, where you see the protocol that is customer edge nodes talk to each other. It has the signaling transport layer, then the SES-to-SES layer, and the host-to-host layer on top, and policy agent. So it retrieves policies from a database. We won't go into that area at all, and then it sort of interacts with the outbound customer switch, interacts with the inbound customer switch, and if there's a policy match, then they will let the hosts send packets to each other, right? Okay, so that's the device-centric view on trust. Sort of what this based on is that we have prior knowledge of what software is on a device, and in limited environments, limited use cases, this is quite feasible, right? If we are doing banking, we know that there's a set of applications that can be used to do banking. Or if it's medical, then also, we don't have like millions of different softwares that can be used. We have a limited set. And in principle, it's possible to know beforehand which are the legitimate pieces of software that could communicate over the network. So we would leverage this knowledge and then use that to exclude any suspicious software from the network. Okay. So what is wrong with IP, routed IP? That is at the basis of the internet. The internet doesn't have authentication. Lying about the source address in a packet level is quite often possible, not always, but it's quite often possible, and it tends to creep in back even if you get rid of it for a while. And as a result, tracing back a DDoS attack is hard and expensive. Domain names in the DNS system can usually not be trusted. The wide area routing protocol BGP version 4 allows, in some cases, route hijacking. And as a result, the hacker could try to do man-in-the-middle attack. We have, in my group, found vulnerabilities in IP and TCP. Okay, they were sort of corrected a couple of years ago, the ones that we found. ICMP applications everywhere, the whole stack is suspect, right? And in the network, we have no separation of control and data planes. So it means that under attack, we cannot even save the control plane. And then when control commands cannot be sent, then mitigate becomes hard. And in this IP network environment, the approach network-wide is to security is quite fragmented. The host owner, possibly a layman in terms of security, is responsible, right? Productivity of the specialists is low. There's little centralization, and thus there's a little automation. Right. Not the kind of automation that would be possible if we would be able to leverage cloud technology widely. And one thing that has long-term bugged improving the security in this environment is that the net neutrality has set unrealistic security, or this law on net neutrality has been based on unrealistic security assumptions. Okay. Then the second view is the network-centric view of embedding trust into the network. It's like, if it's not routed IP, the question is what it could be, right? What is the solution? One possible solution is this SCION called Scalability, Control, and Isolation on Next Generation Networks. This is working software, but not standard, so we can consider it experimental. At the same time, there are real users of this technology already. Swiss banks are sending monetary transactions between themselves, between banks over SCION, right? And it has a production version and it has an open source version, which we tested in my group. Addressing in Skion is based on triple isolation domain, autonomous system, and address. And the addresses in different isolation domains can be, or autonomous systems, they can be different. They don't all need to be IPv4 or 6 or whatever. On the boundaries, we can then translate the traffic suitably and will be fine. In this picture, the red stuff is IP-based internet, and these blue bubbles, they are Skion nodes. And SIG is the Skion IP gateway, which allows IP hosts to communicate over Skion. What does this give? First of all, there are no global kill switches in this system at all. There are no global roots of trust. Only local roots of trust are used for communication. So an isolation domain has a trust root configuration. Every autonomous system within that isolation domain has to agree to the usage of these trust roots. And these are used to, for example, to secure that all root information exchanged is trustworthy. All the names that are supported by the network are trustworthy, and all the packets that are sent can be authenticated based on the source address. Root prefix hijacking in this system is not possible. It has been prevented by the security design of the system. Routing is based on AS autonomous system to autonomous system level source routing, and that gives an immediate multipath to all the devices and highly available services as a result. Recovery from a failure, even this wide area, can be immediate, meaning like, it might take a few tens of milliseconds, like 20 milliseconds or something like that. But that sort of thing is for human, for example, it can be quite unnoticeable. It's seamless. The nodes do not have the routers. Skion routers do not have a routing table because the routing is based on these source routes that are carried in the packets themselves. And as a result, it has very small, fast memory, and as a result, it's a slow power consumption. Right? It can authenticate the packet, every packet, right? You might imagine that running an IES algorithm would take a long time, but turns out that this is not so. Turns out that running that security algorithm to authenticate the packet takes less time than a router needs to run the routing prefix-based search called the longest match prefix search. But every router has to run for every packet. And there's a lot of caching to make sure that remote queries do not need to be done for every packet. We have trust for the names. Spoofing is not doable, and this network has an embedded DDoS mitigation. So this sounds like the thing to do for critical societal services in medical sector, in health, in banking, in industrial use cases where we have, or say, transport automation that is happening over the next 10 years. How to deploy this after productization? Both of these parties, because we have initial products on Skion, but still a lot to do. cooperative security that I mentioned there can be deployed one customer network at a time. We have a sort of a solution for that. I would suggest starting with a limited entry to market. So this net neutrality terminology has this term called specialized network, which is not an internet access service. So this is not for fun, it's for something real, like banking. So we could build these specialized networks which are isolated from the internet. They are not part of the internet, but they would run over the same infrastructure where also the internet runs. And these specialized networks could be introduced in several sectors, and they could be like many specialized networks introduced, and each sector would be probably slightly different, using different security mechanisms that are most suitable for that particular sector. And if we want to do this end-to-end, starting from the user's device, then we could virtualize the device itself, like my laptop that I'm now using. We could run a virtual machine here, and then that virtual machine would have the legitimate applications for banking, for example, separated from the rest of it. And even if the rest of it is hacked by somebody, then provided that the virtualization environment is not disturbed, then this malware will not be able to access my banking data. So the device that gets connected always has a SIM card, and then the cellular network, we have this secure packet data network that we could build, for example, using this KION. So the whole thing would be secure end-to-end, starting device through the firewalls and through the wide area and to the other endpoint. Okay. So isolation is the key to on network level to deliver security. So client service can be related one-to-one, and we have these examples of services, leased lines, Ethernet circuits, MPLS paths that are served by the ISPs. Then we have the end-to-one relation clients, many clients on the same service, like the virtual private network. Many technologies are available for that purpose. In routed IP networks, we have network slicing in 5G, also similar to this kind of thing. But then these specialized networks, and there should be then several providers, several services that sort of basically a bank could say that, okay, I want to be a customer to, say, DNA. Another bank would say that, no, I want to be with Telia. Third bank would say that, no, I would be with Elisa, right? So several providers, but it would be the same network, so that everybody could do their banking over the network, irrespective of which subscription they have, be that a subscriber, end user, or the bank. This kind of thing is not the current practice, but maybe it could be. This is all about end-to-end isolation and bringing sort of the kind of isolation that we have within the cloud between the different virtual machines and carry that to the end-to-end communication from device to device and across the network. So what is the role of the ISP or MNO in this picture? In terms of KION, the last bullet there, roots of trust are managed by the core autonomous systems that form the isolation domain, right? Each isolation domain has its own roots of trust. And those roots of trust help to secure the routing and the names that the network supports and the packets, so that spoofing is not possible. But then we might want to use reputation-based filtering, heuristic mechanisms, but the best we can do when we have IP-based sources. So this requires aggregation of information, and it would seem quite natural that operators would take a role in supporting those kind of mechanisms. Okay. Then mitigation needs a trustworthy party at the remote end, and that could be the admin of the remote firewall, right? If it is sort of like a factory-to-factory network, then these firewalls could be owned and administered by the factory organization, factory IT. But if we are talking about the mobile network, then at least part of this firewalling is done by the MNO. Also, MNO could sell these kind of firewalling services to factories as a platform where the policies would be governed by the users or as a software as a service kind of arrangement. All right. So what I'm suggesting is that we need to improve the productivity of the IT personnel, and that's is the same thing that is happening in the office IT, and we need to bring this into the security area. And with the 5G structure, compute elements in the network, this is becoming feasible now. And also the new regulation in Europe is now more realistic in terms of open internet and security, and how those two things can be supported at the same time. So for the critical systems, what I believe be that in the areas of medicine or rail or aviation or banking or whatever, we shouldn't just put everything onto the internet. That is a bad idea. Securing the whole internet is a huge task, and I don't see why, for example, the banking relations between the customers and the banks should be visible on the internet at all. There is no reason for it. We just okay, it has been there have been practical limitations until now, but now because of the softwareization of the networks, programmable nodes in the network, and because of the compute elements in the network, it's becoming feasible to use the cloud technology to create lots of these kind of specialized networks where we can then provide the network as a service to, for example, to do your banking, right? Okay, so this was my story.